middle of the completeness, arithmetical completeness proof. And essentially, there were two lemmas remaining, but I have to recall the main definitions of a couple of subsidiary lemmas. So what we are doing, we are defining a function g, right, from omega to our model w, and along with the formulas delta of n, meaning there is something like g jumps immediately from w to u after n. Something like that. There is a t bigger than n, such that g of t is u, and for all z of t and d means g of z is w. And I forgot, did I put bars under the letters or
Over.
Over.
Usually.
Okay. Over the letters is good. So over the letters is good. So this is essentially the. So whenever I refer to the elements of the model, they are numerals because it's finite set bounded by a standard number. So that's our delta, and g of 0 is 0, and g of x plus 1 is defined according to the following rules. So let's do like that. So let g of x be w, then define g of x plus 1 by two conditions. So g1 is if it is provable, or rather if x is a proof that lambda u implies not delta w u of n for some less than x, and w are u, and for all z from nx, g of z stays w.
Lambda u was the statement for
Yes,
the limit,
lambda
right?
Lambda u is lim, g is u.
Right.
Alright, so we have two kinds of statements. The lambdas are the important ones, and these play the role of kind of standardized pi 1 statements or sigma 1 statements. Our function reacts to. So our function reacts to the proofs of sigma 1 statements, and among those there are these specific ones. Well, it's a main sort of technical innovation here, I would say, but okay. Okay, then g of x plus 1 is u. So this is a kind of R transition or R move, and g2 is the S move. So here the condition is the following: if there exists an m smaller than x, pi1 formula pi, and u, such that the following conditions are A. So M is a proof of lambda u implies pi. So we are looking at the proof of a pi sentence, pi1 sentence pi, which has got a number smaller than x. That's one thing. Secondly, not pi as a witness below x. So it's a sigma-1 sentence, and there is a computation confirming that it is true, that not pi is true below x. So in some sense, right. The proof of pi from our assumption lambda u occurred at some stage n, but the witness for not pi, so we sort of first acquire a proof, then wait, if we suddenly discover that pi was false, and then we do something, a jump, so to say. That was the idea, but under certain conditions. So this is W as G of M U, and D M is minimal. Possible for among all possible triples satisfying the previous conditions. Among M pi U satisfying A, C, like that. So that's also an important condition. What condition D actually tells us that we cannot make consecutive S moves. We cannot make consecutive S moves infinitely many times, because when x grows, the triples satisfying conditions A, B, and C will be the same ones. So we can only acquire some other triples for smaller m. Right? M was taken the minimal possible. We got new triples, and a move like that can happen one more time, only for a smaller m because of condition D. So that's a crucial point. So we will remember that for the future. A corollary of this will be that actually our function will have the limit, right? So you remember that lemma. So we can make only finitely many R moves because R is well-founded, so conversely well-founded. And so after no more R moves are possible, then there are only S moves remaining. And basically what we will see that by this condition, there could be only finitely many S moves afterwards. So, like that. Therefore the limit exists. So that was one of the points of this, let's say, major conditions we needed to satisfy. And now there was this lemma. Okay, let's auxiliary lemma 1 was about, okay, that was lemma
this
0.
function otherwise remain at that.
Otherwise it stays where it was. Otherwise, yes, if we should say then G of x plus 1 equals u. Otherwise, G of x. Like that. So lemma 1. So if G of x is R below W, then all the previous steps will also satisfy this condition. So this is a kind of a trivial observation by the property of S and R relation in our model. So if something is S of R below this G of X, then it will be automatically R below W. So that's by the frame conditions that we have. Lemma 2. Lemma 2 is the following for all NW. T plus lambda W. So proofs are in T, right? So T is the theory of our logic. Proves that no transition to W by S can have rank less than M bar. And the rank of the transition is this M. M is rank of transition S. Yeah, that was a consequence of small reflection principle, if you recall that observation. So, so these were two things that we will need. Okay, let's go to our remaining claims. So we needed to establish a few properties, and the next one will be this one. Lemma. What was its number? I forgot, but in my notes there are two lemmas, number 4. It's one of them. Let's call it number 6. So if U S W then T plus lambda W proves W conserves over T lambda V. So this is W. And I recall that this statement is essentially, so like phi T psi means for all pi H 1, T plus psi equals pi then T plus phi. Phi, meaning that psi is conservative over phi, like that. Psi is conservative over phi for pi 1 sentences. So, but we in fact here mean the arithmetization of this statement, which is expressed using box T, right? And it will be pi 2 statement, so it's a kind of pi 2 statement for every, if there is a proof like that, then there is a proof like that. So, okay, so we need to prove this this lemma. Okay, so so if U is V, then the statement is trivial because then these lambdas are the same, and this holds trivially, so everything holds trivially. So we may assume U is not real. And of course we are going to reason in T, reason in T plus lambda. Remember this style of nested proofs. So that's nesting number 1. So we are actually giving an informal proof of this statement. So we assume W and T plus lambda V and T plus lambda V proves so by any by one sentence. Okay, so what we can, so lambda W means that the limit of G is W, so we can find sufficiently big number Z such that this happens and this happens. So we can assume actually that the size of this, the good number of this proof is Z, just any number Z. And we may assume that G of Z is W, because W is the limit of G. For sufficiently large Z, we have that. We prove T plus lambda U proves pi. That's what we need to prove. We open the bracket, reason in T plus lambda U. Assume not pi. We obtain a contradiction. Pi. If pi is false, there is a witness. Then there is a C. C is a witness of not pi. Then there is the reason X bigger than Z and C overlying C and C such that G of X equals G of X plus 1. Now what happens here? So we are within this argument inside T plus lambda U. But this, if you have sub-proof or subroutine, actually refers to certain parameters coming from outside. And parameters coming from outside are these, particularly this number Z that we have fixed before. Right? So now we are within this outside argument with parameter Z, and from the point of view of this, it is a numeral. So we are sort of inside reasoning inside box. So this is a numeral. So here we see that X is so there is this number C, sufficiently big that witnesses not pi, and if we are above Z and C, then clearly we are in the limit. In the limit, and the limit here is lambda U. The limit is U. So it's a little bit strange to order it all in your head, but outside we were in the assumption that the limit is W. But now we are inside and we are making a different assumption that the limit is U. It does not actually contradict the other assumption because we are inside the box. Okay.
Because the statement of lambda W is not a sigma one statement. That's the main.
Yeah, well, for various reasons, but it is definitely not a sigma one statement.
One of the reasons that.
One of the reasons that that is not a sigma. But actually, formally speaking, we are not talking about. So yes, if it were sigma, sigma statement implies its own probability. And then we would have necessarily inferred that the limit is z, contradiction, and maybe we are happy. But
just for now.
because we're actually aiming to infer contradiction. But we cannot do that because from lambda w, we cannot infer box lambda w. So that's the point. Instead, we are actually assuming lambda u.
And the complexity of lambda w is pi 2, right?
Right, right. Sigma 2. Because
okay,
G is primitive recursive,
yeah.
There is an answer that for all.
Yeah.
So it's sigma 2. But well, anyway, it's bigger than sigma 1. Okay, so we are under the impression that lambda, the limit is u, we can select an x which is bigger than the standard numeral z, and this witness c. And then we are saying that since the limit is u, but g never reached v. Limit was u. But as we see, practically all the conditions for the jump to v is now satisfied. So, namely, we obtained a certain proof, which is, in fact, wait a second, we have not yet obtained this proof, but we have obtained the other conditions. So, we have obtained the formula pi, which has a witness below that x. Now, from the point of view of z, so m, assume that m is z here. Then we would also have that this w, so g of z is w, and above w we have two nodes, v and u and v, and there is an s arrow from u to v, right? So this one is sort of also satisfied. This one is also satisfied. So the only thing why we wouldn't make a jump, actually, this means that there is no proof like that before, but then it means that we must have, in other words, the only reason maybe I am right. This means, therefore, there should be a move or a move or a transition from u to u with rank less than our number z. Which is impossible, contradicts lemma 2. But let's go over it one matter. Why is the only possibility for G is to jump from U to U with a smaller rank? So let's check it out. Or rather, I would say U to V, U to V, U to V. U will be U to V. So we have a proof, so Z, we call it Z is a proof of pi from lambda V. And we are working in a situation that we know that Z is a proof. So numeral Z is actually a certain proof, namely a proof of pi in lambda V. So this one is satisfied for Z and V. Right. This one is satisfied for Z and V. At least one M we have obtained. Then we obtained a witness of not P, not pi. So, and we have that. WS, what was it? U, G of Z, V. That also holds. So we have here U, S, G of Z, V. Right?
I don't see why A should hold.
Why A should hold?
Maybe
okay, so let's see. So let's examine. So at the first stage of this proof, right? We assumed lambda W, and that actually there is a certain pi1 and selected an arbitrary pi1 sentence which is provable from lambda V. And then Z was the good number of that proof. So we assumed that there exists certain proof Z of pi. Then we selected this, okay. Then we went into this sub-proof, which is a kind of booked proof inside the box. And from the point of view of that proof, Z is now a numeral. Okay, that's important, but anyway, we still know, so this fact is a primitive recursive fact. So if it holds outside, it will also hold inside, but with numeral Z. It's sigma completeness. So by sigma completeness, T plus lambda V, Z is still a proof of 1. Right, so that's we cannot avoid. So this one is definitely true. That means for M equals Z and for U equals V. So
yeah, but okay, so it should be a proof for lambda U implies pi, but it's a
right.
proof of pi.
Okay, agreed. So let Z be a proof of lambda implies pi.
Okay.
So
And
let Z be
okay.
T Z lambda V. That's good.
Okay.
Fair point. Yeah, there is a slight difference in Gödel numbering there, but nothing changes in substance. So this condition is satisfied, this condition is satisfied, this condition is satisfied for Z again and V. So it would have made a jump from U to V. No. But it didn't jump. How is it possible? Because it was not minimal. And if it was not minimal, that there must be some other, actually some other triple for which forced it to stay in U. There should be a transition from U to V. Okay, so unless there is a transition from U to U with rank less than Z. We can say that at Z. Unless there is a transition from U to U with rank less than Z, then it's forced to stay in U until we exhaust all possible. By small reflection, this is anyway not possible. By lemma 2, right? So by lemma 2, there is no transition to W with less rank less than standard number. This is a standard number. Like that. So this closes this subproof and simultaneously the whole proof. Like that. So this is the kind of analysis that we are into here. So let us try to, let's now embark on the last part of this story. This was actually the easier of the two cases. Now we are in the central sort of case. Okay. Suppose W are U and V is the subset, and for all V in V, not U as W. Maybe like that. And we claim that T plus lambda W proves that it is not true that lambda U conserves this junction.
Sorry, could you remind me that what was the properties for T that you assumed? Oh, T, which requirement you
T
assumed?
was a theory containing I sigma 1.
Okay.
Re containing I sigma 1. So it can reason about primitive recursive functions freely, and it can also minimize sigma 1 statements, as we, by the way, probably, maybe we did it here, but maybe no, this was a minimization of a bounded set. But anyway.
Any RE theory containing I sigma 1 would work.
Right. We call it Gödelian theory containing I sigma 1. There's an enumeration. Oh, so this is the running assumption. It is interesting to know how far below we can go, but so there were some improvements, but not very radical. Like, it's still not EA, but something like EA plus parameter 3 by 1 induction, as far as I know. So it's considerably weaker, but nevertheless
far above EA itself.
Still a little bit above EA, yes. Not far. Anyway, so but this is, I would say, academic interest. It's not that important. So also to note that this V, in some sense, this quantifier over V is a bit fake, because the larger the V, then the weaker this sentence. And so basically, if one takes all possible V such that U not as WV, the maximum, then that will be the statement that we are proving. But somehow, Japaridze formulated it in this way. Okay, no problem. So, okay, so proof. Proof. The reason in T plus W, and assume that for all Z bigger than N, G of Z W, and then G of n is W, of course, as well, but also, and T proofs with G of n is W. Because that's a primitive recursive statement. Sigma 1. So T can prove this. So n is, of course, this number after which it is in this limit. So, like that. So we fixed this number n. And now what we can claim is that T plus then T plus lambda u does not prove not delta w of n. Because if it does prove it, then it must make a move to u. Otherwise, G moves to u by r. So the rules of the game are such that if one obtains a proof like that, and eventually we will obtain it, then we must go from W to U. That's it. So therefore, since we are staying in the limit, therefore this is not true. Okay. We need to show so. We need to show, or it is sufficient to show that for all V from V, T plus lambda V proves not delta of n. Why is it sufficient? Because if we prove that for every V, then we can prove not delta W of n from the disjunction. And this will be a pi1 statement witnessing that this one is not conservative, because we have found then otherwise then not delta of W of n is the pi01 statement witnessing non-conservativity. Because this means that there exists a certain pi1 statement which is provable here but not provable here. So we have found something which is not provable here and need to show that it is in fact provable there. And then we are done. So very, very nice. But so you see, here we see the role of these deltas, because they give us somehow a family of pi1 sentences sufficient to establish non-conservativity whenever we need it. So that was the tricky part. So that's, yeah, at least I see it this way. Okay, so we consider any V from V. Then such that you not as V is not as reachable from U by SW. Okay. clearly. And then V is not SW. Automatically, we also have this. V itself is not. Sorry. What I'm saying then.
It cannot.
This is yeah. Then U is not V. Because otherwise, if they were equal, this would violate reflexivity of S now. Okay, so that's preliminary, and then we go to the main argument. So let's fresh screen for that. Right. Okay. And we are going inside the box. So reason in t plus lambda 3. So we are showing this thing. Inside the box for a given v. Reason in t plus lambda v. And assume delta w u, and we are reasoning towards contradiction as always. If delta, that means that what was delta? Delta means that our function jumps from w to u after n immediately. So basically we say when we know that there is a t bigger than n, right? Such that g of t is u. And for all z, such that n is less than z less than t, g of z is double bar. It's very pleasant to go over things slowly. You need to really go very, very slowly. So, okay, this is so that's what we get from delta. Delta means that there is a jump at a certain point t
To the u.
to u,
Oh,
and everywhere before that, from n up to t, our
it
function
is still
was
undoubled.
was in w. So that's correct. Okay. Mm-hmm. Yes, but so that's what we have as our sort of prehistory up till the point we came to W. But we know that eventually we ended up in V. So basically, the evolution was like that. So we were in W. So that happens from n from time n to time t minus 1. Then at time t we jumped to u, right? At certain time t. And then there was another unspecified piece of evolution until we ended up in V. And strictly speaking, we don't know how many steps and or nodes we used here until we ended up in V. But let it happen at the time t prime. So we first reached the limit. Okay. And by the way, V was not U, right? So that was our assumption here. Okay, so let's denote these stages somehow. And I'm using the notation from here. So x1.
Sorry, I'm a bit confused. Why you consider V is not SW accessible from U there? Well, why you only consider?
Because in this lemma, we need to consider only those which are
okay.
not SW.
Okay.
So that's kind of
Well,
a crucial
lots of
point.
conditions.
Crucial point. But we're only using here, let's say, a tiny consequence of that, namely that it cannot be U itself.
Yeah.
Right? So if it's
Because
itself,
it's
nothing is correct here. Right? So in that sense, and so, let's see. So until we ended up in xk, which is t prime, and x0 is x0 is t, like that. Maybe we should simply call them t1, t2, etc. would be natural, but okay. Okay. So, and these nodes will be to which we jump. So these are the moments where we jump to certain new elements of our model, right? And this UK will be V. Okay, that's the situation. So UI is J of X. UI is J of X. And now we will kind of analyze what is possible on this path from x0 to xk. Okay, what is possible? So for this we select let J be minimal. After which U0 does not see UI for all I bigger or equal J. In other words, look at this evolution. There should be or rather maybe, okay, so we need that. Okay, so firstly, we know that this U0 is not R related to UK because if they were R related, they would be also S related. But they're not S related. So no R relation here, and we select kind of the first one for which there is an R relation, or in other words, select such a J so that beginning from J, there is no R relation between U0 and UI larger than J. And since it is minimal, we also have something like U0 R Uj minus 1. unless,
J is just 0.
yes, exactly, j minus 1 is 0, something like this. Okay, so that's what we have. So let's so we selected this j, apparently it exists. And we notice that after this j, there cannot be any r moves. There are no r moves after j. Now the question is why? Who understands why this is so?
Well, because of the condition on the frame that if it is, then that should be also R accessible from U, not?
Right, so we had this then, right? So if there was an R move somewhere after, there will also be an R relation between that point and everything on the path before, including U0, but this is not the case. So, so there cannot be any R moves after J. And by the way, J can also be equal to T prime, so equal to K. So that's also a possibility, but okay. What does it mean? That means they are all hence all moves after J are as moves. Right, so the function jump, but after the last one there will be only S moves. But and the ranks of rank less than x0, of rank less than x0, because if there were any S move of rank bigger than x0, that means that there will be R relation. So there will be R relation between, so if let's say what was x0 was t, right? And in t we were right from n to yes. Yes, if ranks were bigger than x0, that means that this S move, so look at this condition. So L is this rank, right? So if rank is M, that means that we are moving from W to U, let's say, from one node to another by S, with respect to the point G of that rank. But that rank is actually already T. So this means that we are already in W, not in, we will be already in U not in W. And then we must have an R relation between these points. So there will be something like, there has to be an R relation from here and to the next one. And here will be an S move that we consider. But this is not possible by our selection of this J. So that's that gives us the following, that all the ranks of these S moves had to be below x0, had to be below x0. Right. And therefore, in the interval from n to x0, to x0 minus 1. So why are they bigger than n? Because S moves cannot have standard ranks, so they have always non-standard ranks, and n is a standard number. So n was our point where we selected the point after which. So this is a prehistory from n from W to U. So that was this standard number n. Okay, so the ranks of S moves have to be here, right? Okay.
Why? So why can't the rank be xj or something?
Why can what?
So
right.
hence all the moves after j are S moves of ranks less than x0, but why can't it be xj? Let's say.
Right.
Or maybe
So firstly, we are talking about S moves after J, right? So we are actually considering this uj minus 1 as uj as uk. So that's the part of the evolution that is of interest to us. So we have already established that these must be S relations, not R, right? So that's one point. Because we selected J in this way. So if it were R, then it would be. So anyway, but now consider this move. Consider this move. So if it has certain rank which is bigger or equal as 0, that means that at that point our function j, so rank, let's say, call it m. So at that point m, we must have the following, that g of m r uj and g of m are uj plus 1, for example. Because of the condition for the S move with rank m. So if it is rank m, so j must be at the following point, which is r below uj and uj plus 1. Right. But it isn't below uj plus 1 by
because J was the minimum.
By the selection. So that was the. So essentially the same kind of reasoning, that there are no R moves after J. So there are also no S moves with ranks bigger than x0 after j for the same practically structural reason. So our relations kind of
But I
surround it.
yeah,
Mhm.
I feel that there are some details. Well, maybe,
No, I guess
maybe
every
I'm-
Yeah, well, okay. Well, we still have time to finish. So we are kind of in the middle of this, but really 2 lines. We have to suffer for 3 more lines. but let's go back to let's kind of review what we have done in this book, right? So firstly, what are we proving? Right? So we are proving that assuming lambda v and assuming that our function moved from w to u after n immediately, right? We are sort of deriving a contradiction. So that's what we need to show. Okay, so we selected a certain number t bigger than n. So n was this bound on the move from w to u, right? So that's an important thing. So at the point n, we were in w, and then sometime after we moved immediately to u. So that was the first structure. So that was one thing. And that happened at the moment t. Then we said, okay, eventually, assuming lambda v, we eventually arrived at a certain point v, different from u. So that was. Now we are saying, what could have happened here on this way? So there could be, theoretically, there could be r moves or s moves. So something we don't know yet what. And then we kind of selected the last j for which there was an r relation between u0 and uj minus 1. So after that, u0 does not see by r any of these uj, right? So u0 does not r see ui for I bigger than j. So that's it. So one such point must exist because the end of this interval
Is not R accessible.
There is no r. Okay, good. So j is kind of legally defined by us. So there is this point, certain point j, and then we are telling certain, making certain analysis about this. What happens after j? So we are now focusing on what happens after j, namely on this part of the story. And firstly, there are no r moves. That we sort of explained. If there were, there would be something wrong there. Okay, now, so there are only s moves. And now we need to kind of show that these are the same s moves for the same kind of, with the same kind of rank. And then this is not possible. So ranks must be decreasing. Okay. Anyway, so let's see. So what certain s moves. So every s move is determined by, indeed, its rank L. So it happens when we obtain certain proof, a certain witness, but also these proofs and witnesses are concerning the points connected by S with respect to this G of M, where M is the rank. So the crucial question is, where is this point G of M, right? So assume that this rank is M for a certain S move. And the question is, where is this point G of M? And what we know is that these two things, G of M must be R below both points, where we start and where we end. So there should be some R relation. Okay, but recall that we postulated that there are no R relations. So if there is an R relation to any of these uj, by this lemma, there will be an R relation to anything in the evolution which is before. So if there was an R relation here, there will be R relation to anything that was before. But after uj, we don't have any. After uj, we don't have. Right. If there was R relation here, there will be R relation here, and then there will be R relation in the previous point, blah, 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 and then we end up going down, going down, going down until we reach U0. But there is no relation between U0 and so.
So there will be an R relation between U0 and Uj.
Yeah, that's what we want to eventually say, but wait a second. So,
Yes, but
R relation between U0 and Uj?
so it's by lemma 1, right?
but we are arriving at a contradiction, right? So that's
okay.
so of course there cannot be, but that's what we want to. So, but now we are saying so. The only thing is that we are saying yes. So once again, so of course, once again, so we are actually claiming that the rank should be less than x0. So this m should be less than x0. So if it is bigger or equal x0, then this j of m occurs is one of these xi's. Is one of these xi's. And it cannot be any of these xi's, because if it is one of these xi's, which is r related to something there, we would also have
This
our relation from 0 to the same point. And this is excluded by this, this principle. Right. Like that. So there was no relation by r from u0 to anything after uj. But this also means that there is no r relation to anything here from any of the previous, any of the lower any of these points after, because we can go down always. So like that. So our moves are, our relations here are totally excluded. So the rank must be less than x0. But it also is always bigger than any standard number. So it must be in the interval from n to x0 minus 1. Okay, and now we look at this interval from n to x0 minus 1. And this means, here, j of z equals double. Right, so it means that we are here. From n to x0 minus 1 is t minus 1, so that's g of z here equals double. So that means that here we can safely put w. So before this analysis we didn't know what kind of ranks are here, but now we established that the ranks are in this interval. So there SW moves. Right. There SW moves. Yeah, so we are done. Let's finish the argument. So what I will do, I will like that. Right. So what we see is let's erase this superfluous thing. So here we have this uj. And this is SW. Moves all the time. Moreover, from uj minus 1 to uj is also W minus 1. So we have the following. Either recall that this uj, there are some degenerate cases when this uj is simply u0, right? So that also needs to be taken into account. So we have either u0 equals uj minus 1 or u0 are uj minus 1. Why so? Because recall that uj was the minimal one for which there was no such relation afterwards, so for this one we did have it. So either uj minus 1 is u0 or uj minus 1 is reachable by r from u0. Okay, which means that u0 SW also uj minus 1 SW R arrow implies S arrow for any S, including SW, so we have from U either by reflexivity or by S arrow we reach uj minus 1, and then we go all the way to uk. That means that there is an SW arrow from here to there. And what does it mean? That we obtained a contradiction because we started from the assumption that there was no arrow from U to V.
In the assumption of the lemma.
And we actually produced an arrow from U to V. Very strange, but so it worked. So let's go quickly one more time. So the whole proof of lemma 7. So the first steps were very clear, right? So we simply can pinpoint. So we, assuming lambda w, we fix a certain number n where we arrive with this w, and we notice that there cannot be a proof from lambda u, negation of this delta formula. So there's a kind of counterexample to conservativity. So all we need to show is this specific thing, that for every v from our set B, which is not related. The only thing we know is that V is not related to U by SW. We must show that there is a proof of negation. And this is what we are doing here. So we embarked upon this proof, assuming the contradiction that there was a move, and then there was this very detailed analysis of what happened in this way. So it was this piece of prehistory where we stated W, then there was this U, and then there was kind of evolution up to UK. And what we actually managed to show that all of that could only be the SW moves. So in fact, there was a rather restrictive kind of behavior. Only SW moves, nothing else. So that was the outcome of all these considerations. And if all of them are SW moves, then clearly there is a SW relation from here to here, and that's a contradiction. Like that. So yes, so that's. I think that this is one of the most tricky constructions in probability logic that exists. There are different versions of it, but this is more or less the champion of trickiness, as you see. So there are other maybe only slightly less tricky proofs, but this one is a good one. So you cannot. So the only thing to do is you need to kind of live within this construction for a long time to understand what's actually going on there. And of course, the trickiest part was to invent these conditions that would somehow, by fixed point, ensure this kind of behavior. So this was the thing. Right. Yeah, it's time to stop. But one thing I perhaps finish with is that so this arithmetical completeness theorems, they are we are finished. There will be
in 5 minutes.
So anyway, they're kind of a tool to produce counter examples or examples of arithmetical sentences with various interesting behaviors concerning conservativity or interpretability. For example, if you would like to construct ORI sentence, like a sentence phi such that PA is considered conservative over PA plus phi and simultaneously PA plus not phi. So you can do that now without any fixed points, but just by producing a Krivki frame for ILM, which would ensure that this is. So you need to write down a specific formula that will be false in a Krivki frame, and then you can. That would ensure that the counterexample of this formula would actually be a phi satisfying these conditions. Okay, so that's it. So let's stop here. So anyone in
5 minutes to the end of this. Any questions online?
No.
Okay.
No, thank you very much.
Okay. Till next time.
What is the
Do we have
next?
Do we have some next session also? And what is it going to be?
What was the date?